Hello, Amal is here. In this video, we will discuss about some cases from the real life related to the mechanics of materials force. Firstly, I will explain some terms related to the cases which we will discuss in this video. Axial loading. Axial loading is better understood as application of force on a structure directly along an axis of the structure, and a common example is the axial loading on shaft. Torsional loading. Torque is a moment that twists a structure, unlike axial loads, which produce a uniform or average stress over the cross-section of the object. A torque creates a distribution of stress over the cross-section, and for example of that, the structure which with a circular cross-section, often called rods or shafts. And when a torque is applied to the structure, it will twist along the long axis of the rod and its cross-section remains circular. Stresses on the beam. There are two types of stresses can apply for the beam. Firstly, the normal stress. The beams get a normal stress in the lengthwise direction, which is vary from a maximum in tension at one surface to zero at the beam's midplane and to a maximum in the compression at the opposite surface. Therefore, the beam that exposes to a positive bending moment will tend to establish a curvature of concave upward. And the second type is shear stress. A normal and shearing stress results in the beam when the beam is exposed to a transverse loading. So, the shearing stress in the beam is the stress that happens due to the internal shearing of the beam that results from shear force subjected to the beam. There are three cases we will discuss in this video. The first one is workout, pull-up bar, and the skateboard and dental implant fixture.
Alright, hello. Assalamualaikum. So my name is Muhammad Ikmal. So I will talk about LO1, about the axial loading and also torsional loading in real life example. Alright, so for axial loading, we pick a lift up bar, which we put it between a door, so it will stuck in the middle. So this is the measurement and the force needed to hang the bar between the door to make sure the bar does not fall. So we do not know the bar will fall or not, so we have to measure the stress, the reaction force into the wall. So this is the free body diagram, same just like before. So just add RA and RD because it is fixed and does not move. Right, so this is all the information needed. Both end are fixed. Yeah, you can read it from the picture above. Just the material used for AB and CD is steel. So just the middle part is aluminium. So that's all you need to know. And also for the cross section, for steel 2 inches square and aluminium 4 inches square in the middle. Right, next we move to calculation. Alright, first of all, first step, we fx equal to 0. So if fx equal to 0, we get Ra plus Rd is equal to negative 100 Newton. Why there's no Fy? Because Fy is not exist, no force in the y axis. So that's why no y axis. Right, and then we cut each segment piece by piece. Alright, from to calculate the pressure, so we cut from between A to B, we cut it and then calculate the PAB and then we get the RA, and then make sure the make sure the pressure is directly is opposite from the R, from the what we call it, from the reaction force of the A. Alright, make each part and then equal it with the RA, so we will get a equation that we can use later on. Alright, so next, from the information from the all the pressure we get, and then we use the formula mentioned here. So it is a formula, P times with L divided by cross section times with the E, or the Young modulus, and then plus all of the segment and then equal to zero. Equal to zero because the bar will not change in length because the door will not move. It is fixed, so that's why. Alright, so we get RA is equal to negative 129. It is negative because the force is to the left, and RD we get 29.412 because it is positive. So this is proof that the bar will stick and does not move, just stay up there with this kind of force. Alright, next, for torsional we use screwdriver. So this is the measurement, and also our measurement, our cross sectional, we have measured the torque and also the um, length of the screwdriver, all we have measured. And then right, so this is our free body diagram. We include TA there because it is fixed. It is the place we put our hand, so it is fixed, so it is a reaction force and also torque. So we need to find the TA first. Alright, so this is all the information about the screwdriver. It just the segment A to C from right to left, and then the handle is made of rubber with the Young modulus 0.1 GPa, and also the rod is made with steel with 215 GPa. Alright, bear in mind. Alright, next, how to calculate it? Just same with axial loading before. We need to all the torque, all the sum of the torque is equal to 0. So TA, the TA is in opposite direction, so it is minus. So send to 0 and then equal to TA. That's why TA is equal to 734.5. And then cut part by part from A part to B part. From between A to B, cut it, and then we get the stress for the segment, the torque for the segment. And then from B to C, cut it, and we get the torque between the segment. And then we use this information to get the stress, and then we get stress AB and stress ABC there. And then from stress we get the angle of twist. So this formula angle of twist there, as stated there. So as you can see here, the angle of twist is small, so that's mean that if you turn the handle, the rod will move too, because it will not move from the handle, it will not move away. So that's mean that it stick together, does not easily move when you use the screwdriver. Right, that's all from me. Thank you.
Hello everyone, today we're going to be looking at the skateboard, doing some stress analysis on it as well. Okay, so the skateboard is much similar to an overhanging beam, which we will be using as sort of our base to analyze the skateboard. So as you can see, there's supports in an overhanging portion. In our skateboard, we also have supports which will be simulated by the wheels, and the overhanging portion is these areas you see to the far left and the far right. So for our weight distribution of the person, after doing some research and reading, we find that the perfect, or you'd say the best stance that a skater has, is when they have about 60 to 75% of their weight on their front foot. So this allows for them to have their center of gravity closer to the center of the skateboard and allowing them to control it. So when we do our calculations later, we're actually going to put 60% of the person's weight in front and 40% in the back. So this is our free body diagram. So what we actually have is these two, which are the person's front foot and the person's back foot, and these are two wheels and their reaction forces. What we actually used was 70 kgs for the person, which is about an average weight, and then we managed to convert it to newtons, which is about 690 newtons, and then we have our front foot and our back foot with those forces distributed. So overall length of the skateboard is about 0.78 meters, about 78 centimeters. That's the average professional full-size skateboard. From that, we can plot our shear force diagrams and our bending moment diagrams, where we can see things like the maximum and the minimum bending forces, bending forces and moments, and the maximum and the minimum shear forces. So this maximum bending moment is what we're going to use to find our bending stress in our skateboard. Right, so to actually find the bending stress, we have to find the moment of inertia. So our cross section is rectangular, and it's quite simple finding the moment of inertia, converting it to meters, and eventually finding our stress value. So from looking at the skateboard, we can see that in this area it's going to bend downwards. So we can easily assume that it's going to have a positive bending moment with compression at the top and tension at the bottom. And since our cross-sectional area is symmetrical, we can also assume that um, our compression and tension forces are equal in both sections, with this being um, the line of the centroid. So that's about it for the skateboard analysis. Thank you very much.
According to research, using softer or more known as lower rigidity crown material reduces the stresses generated on the jawbone, the cortical and spongy bone that is, and that it absorbs more energy from the applied load and transfers less energy to the following parts of the system: implant, abutment, complex and bones. Vertical and oblique loading conditions are exerted on the upper first premolar, the dental implant fixtures referred to as the crown and the jawbone, and implant itself are observed for the stress and deformation when the force is exerted on the said sections. It is shown how crowns made out of different materials withstand the force exerted on it. The cortical bone has a Young's modulus of 13,700 megapascal with a Poisson's ratio of 0.3. The trabecular bone, on the other hand, has a Young's modulus of 1,370 megapascal and a Poisson's ratio of 0.3 as well. This is what the natural structure of the human jaw can withstand. However, the implant and the crown are made out of a few materials. The crown is made out of in cream, which has 418,000 megapascal with a Poisson's ratio of 0.22. Acrylic, which is made out, which has a Young modulus of 2,800 and a Poisson's ratio of 0.28. Porcelain, which has 68,000 megapascal with a Poisson's ratio of 0.35, and nickel chromium used in crown for 249,000 megapascal with a Poisson's ratio of 0.32. The implant itself is made out of titanium, which has 110,000 megapascal Young's modulus with a Poisson's ratio of 0.35, and a glass ionomer, which is the cement layer, which has a Young's modulus of 12,000 megapascal with a Poisson's ratio of 0.25. The load exerted on the implant was done with 150 Newton twice, 100 Newton thrice, and 400 Newton once. And the stress and deformation is observed. So as we can see from the table, it's observed here that the maximum strain is experienced by the crown followed by the implant. The deformation shows that the crown is the most affected part of the section and when it comes to dental implant fixtures.
So, we have reached the end of the video and we hope you enjoy watching. Thank you very much.